Okay, so going back to the grid, we can highlight those systems that were based on MapReduce itself. You know, the MapReduce paper itself in 2004, and these language layers on top, Pig and Hive in 2008, where Hive is SQL and Pig is a relational algebra looking language that we'll talk about in some detail in the next few segments, and Tenzing, which is also SQL, and Impala, which is also SQL, where Tenzing is from Google and Impala is from a company called Cloudera that's a pretty eager evangelist of MapReduce and Hadoop based technologies in general. Okay, so one trend I think you see is that these declarative languages on top of the parallel processing primitive of MapReduce are really here to stay, right? So people that were relatively against these kind of languages are certainly doing it. Now, it's also fair to say that the enterprises in general have made a pretty significant investment in SQL expertise. So even if they're attracted to the advantages that Hadoop might bring, they're pretty much demanding SQL. So this may be a response to this inertia from having invested in SQL in the past. I think that's certainly true. However, it's also true that the desire for declarative language is reasonably well founded for reasons that we've already talked about. Okay. So you can put these systems on this timeline, and the only point I want to make about this is that there's a bit of a gap between the paper in 2004 and these systems in 2008. But then as soon as you had Hadoop, the system itself, developed at Yahoo and released as an Apache open source project, you sort of immediately see an ecosystem start to emerge of extensions to it that add these, in particular adding these languages on top. And so I think that the need for a high-level interface is motivated by how quickly they came around as soon as Hadoop was out. And again, it didn't stop with these later systems a few years later. Okay. And actually, you know, not on this page, there's potentially hundreds of, if you include, you know, research projects based on extensions to MapReduce, there are really, really a lot. Okay. And so this is some of the most popular ones. All right. So another subset of this grid that you can look at is just the NoSQL systems. Now, the whole last few segments have ostensibly been about NoSQL, but I've also included these kind of analytic systems in here, MapReduce-based systems and a few others, for example, Dremel and Spark and Shark. Dremel is a system from Google that is the back end of a query as a service system called Google BigQuery, which is pretty nice. I'd recommend taking a look at it. You can sort of upload data and put it in there, and it doesn't matter how big it is, and you can kind of query it at very low latency speed. Spark and Shark come from the AMP lab at Berkeley and are part of the Berkeley Data Analytics Stack, BDAS or BADAS. And Spark is a language level on top of, it's not MapReduce, but on top of a parallel processing system. And Shark is an SQL layer even on top of that. Okay. And so a couple of the distinguishing features of Spark is it loads everything into memory, processes everything there when possible, writing things out to disk only for fault tolerance reasons, so much less often than MapReduce. And it also supports iterative processing, which is pretty important, and we're going to come back to that a little later in the course. And then Shark again is just SQL on top of this. All right. So within these NoSQL systems, one thing you can look at, there's not much I want to say about this diagram, except that, you know, to point out that there's been this sort of the Cambrian explosion. So first you had sort of Memcache, which is again just a caching layer for really the real system, and the real system was a bunch of MySQL databases that weren't really working all that well for the requirements they're having them used for. But you could bring things into memory and keep it there, looking it up by name, and it was just sort of a performance enhancement, a free performance enhancement if you invested in this system. The real, you know, approach of throwing out everything you have and replacing it with a NoSQL system came a little later. And so the only couple points I want to make is that there's been kind of a Cambrian explosion of different systems around this time, and that, you know, this space in here is not nowhere near as empty as it looks. I've picked out a few systems here, but really the emergence of new systems in the space hasn't really slowed down much at all. So really filling out the design space here since around 2006. And the only other point I make is that these quite popular document oriented data models systems, CouchDB and MongoDB, have actually been around for quite a while. So they've been, the original release are 2005 and 2007. So sometimes I think they seem like newer systems, but they have some maturity. Okay. So then finally, one of the points I want to make is about this column that I've called joins and analytics. And so one of the distinguishing features of NoSQL systems is that they typically don't support any notion of joins, and many of the proponents of these systems would argue that that's okay, that the joins aren't really necessary. So the argument about why you can get away from joins goes something like this. When you're joining two tables, you sort of have one record and then a bunch of corresponding records in another table. Well, if I put all those corresponding records and co-locate them with the parent record, right, then I can access everything all at once, and I don't actually need to compute the join. Okay. So that works, and it should sound somewhat sort of familiar because it was part of these network and hierarchical data models that we talked about in the discussion of how we motivated relational databases. And if you remember that the downside of this was that you had kind of one dominant access path into the data, but any other access path was either not supported at all or was inefficient. Okay. And if you wanted to reorganize your data to support a different access path or because your needs changed, well, a lot of your code might have broken and you would need to sort of rewrite it. Okay. And so this tension between buying yourself a little bit of performance by organizing the data in a pretty rigid way versus the development time that you save by not having to rewrite your code whenever you want to reorganize the data, that equation sort of balanced a certain way in the early 70s, and I would claim that it still balances the same way now. Now, this is not to say that commercial databases, relational databases as they stand today, are necessarily meeting everybody's needs. I think they're clearly not for a variety of reasons. But to sort of throw out what we know and give up on this flexibility that was earned from the relational data model in favor of kind of upfront decisions about one dominant way of organizing the data, I'm not sure that's the right one either. So that's one point I want to make. Another point is that there's not necessarily one right way of decomposing things or one right way of even evaluating a join, even if you support them. Okay, and this is a point I've made before, but I want to bring it up again in the context of NoSQL. So in a pretty classical web application scenario, if you want to show all comments by a user named Sue associated with any blog post by a user named Jim, there's a couple different ways you could do this. You could look up all blog posts associated with Jim and then fetch all corresponding comments, filtering for Sue. Or you could go the other way. You could find all comments by Sue, and then for each of those comments, look up all the blog posts by Jim. And either one of these ways may or may not be available to you if you've already organized your data a particular way. But even if they are available to you, it's not clear which one's the right one. And there may even be a third method that sounds a little wild, but it's filter all comments by Sue and then independently filter all posts for Jim, sort them by some sort of blog ID, and then pull one from each list and walk over the data that way. So that sounds a little wacky, but that's just a sort merge join that you may or may not be familiar with. And if you're not, that's okay. But the point is, all three of these are perfectly valid, and the right one depends on the details of the data that you as a programmer, as an application programmer, may or may not have access to, and that may change from time to time. And so really only the system is equipped to make this decision. And so being, sort of succumbing to the tyranny of the initial design decision at the time the database was built or designed is one problem. Another problem is that even if you have some flexibility, leaving it up to the programmer to make the choice over the right way to access the data is asking them to make a decision for which they aren't equipped to make. Okay, and so this is something that does not happen with relational databases. Neither one of these problems exists in the same way. Okay, so I think trying to inject some of that smarts back into these NoSQL systems is a good idea, and we see that trend happening. Okay, so that's maybe the takeaway that I want you to have. Okay, so that's all I want to say about this grid, but let me give you a little bit of a character of a response to NoSQL by Mike Stonebreaker in Communications of the ACM. And there was a couple of different blog posts here that talked about two different arguments in favor of NoSQL, and they responded to each one of those arguments. And so I'm mostly going to focus on the second one. So those two pro NoSQL arguments are these, where he sort of points out that there's two value propositions offered by the NoSQL community. One is performance, and the story, as Mike says, that I more or less agree with, is that these people started out with a MySQL deployment of some kind, and they had a hard time scaling it out in a distributed environment. And then they had two choices. Either they could invest in a large-scale relational database and pay corresponding license fees, or they could do something different, use one of these NoSQL systems. All right. And then the flexibility argument is like, well, look, my data doesn't conform to a rigid schema. So in the performance argument, I'm not going to spend too much time on this because we talked about the trade-offs associated with different choices in transactional guarantees in these various systems. And the other part of the argument that Mike makes has more to do with database internals that we didn't necessarily cover. So let me focus on the flexibility argument. So an observation that he makes that I think I'd probably agree with is that, who are the customers of these NoSQL systems? And so it's a lot of startups and a lot of web startups. And it's not quite such the same penetration in the enterprise, okay? At least not yet. So why is this? Well, one argument is that most of the applications in the enterprise are traditional OLTP, and if you don't know what OLTP means, online transaction processing. And so these are sort of bank records, right? Things where getting the transactions right really matters. Okay, and it's OLTP on structured, organized data. And so there's a few other applications around the edges, but they're perhaps considered less important, right? It's okay to take a high-risk system because the application itself is of less interest to executives. Okay. And so really no ACID compliance, no transactions is equivalent to not much interest in the system. It's not okay to screw up mission critical data, but for that for some other application around the edge, maybe it's okay to experiment with a NoSQL system. Okay. And then second point he makes is that, relying on these low-level query interfaces is a real tough sell. And he calls up Codacil, which is an early data manipulation language that predated the declarative languages that we've been talking about. But we've sort of been down that road, and it's tough, and it's why these higher level languages were invented. And again, we see it with MapReduce, which is admittedly analytics as opposed to pure NoSQL, but we see that the value of these higher level interfaces pays off. Okay. And then the third point he makes is that, NoSQL means all bets are off, right? There's no sort of homogeneity at all between all these different deployments. And so if in a typical enterprise you have maybe 10,000 databases, you already have enough of a trouble trying to integrate data from these databases because of the heterogeneity within their schemas. But at least that you're always working with rows and columns, and at least you have kind of a standard interface to manipulating them. Okay. And so having the number of design decisions that you have to make to encode your data in one of these NoSQL systems, what becomes the key, what becomes the value, are the blog posts nested under the comments or the comments nested under the blog posts, right? Do users keep their own wall, or do the the messages on their front page, or does the person who wrote the message keep access to it, or both, right? All these different design decisions of nesting layers and so forth complicate integration and complicate standards. Okay. So it's a tough sell. The other point that I guess I like to make that's related to this third one here is that there's no real free lunch, right? Either the complexity is going to be in the system that you use to model the data, or you're going to sort of hand it over to the application. But in some sense, they're always these schemas, right? This application business model is going to be encoded somewhere. So having it centralized in the data system as opposed to hidden more than once in various applications that access the data system seems like a good idea.